derating of parallel conductors is necessary because of the increased heat that is generated when multiple conductors are carrying current in close proximity to each other. This is due to the fact that the magnetic fields generated by the current flowing in each conductor interact with each other, creating additional heat. The amount of heat generated is directly proportional to the number of conductors in the raceway, so the more conductors that are parallel, the greater the derating that is required. Consider the example of using 4/4/0 conductors in parallel to feed a 420 amp load. This would require a derating factor of 0.8, which would result in an ampacity of 260 amps per conductor. This is because the 4 conductors are carrying current in close proximity to each other, which creates additional heat. The 600 mcm copper conductor, on the other hand, is a single conductor, so it does not have the same issue with heat generation. This is why the 600 mcm copper conductor can be used to feed the 420 amp load without derating. It is important to note that the derating factor for parallel conductors is not a mandatory code requirement, but rather a recommendation from the National Electrical Code, or NEC. The NEC does not strictly require the use of derating factors in all cases, but it does recommend that they be used in order to ensure that the conductors are not overloaded and operate within the safe temperature limits. To understand this better, let's delve deeper into the concepts of ampacity, conductor sizing, and the factors that influence heat generation in electrical systems. Ampacity is defined as a current, in amps, that a conductor can carry continuously under the conditions of use without exceeding its temperature rating. This rating is crucial for ensuring the safe and reliable operation of electrical systems. The NEC provides ampacity tables, such as those found in NEC Table 310.15b16, which list the ampacities of various conductor sizes based on their insulation type and the ambient temperature. These tables serve as a starting point for determining the appropriate conductor size for a given load. However, the ampacity values listed in these tables are based on specific conditions, such as a limited number of conductors in a raceway or cable, and a specific ambient temperature. When these conditions change, adjustments to the ampacity are necessary to account for the increased heat generation. One of the primary factors that affects the ampacity of conductors is the number of current-carrying conductors in a raceway, cable, or enclosure. When multiple conductors are bundled together, the heat generated by each conductor can raise the overall temperature of the surrounding environment. This increased temperature reduces the ability of the conductors to dissipate heat, leading to a decrease in their ampacity. To address this issue, the NEC requires the application of adjustment factors when the number of current-carrying conductors exceeds a certain threshold. These adjustment factors are found in NEC Table 310.15 and are based on the number of conductors. For example, if there are 4 to 6 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its value as listed in the ampacity tables. If there are 7 to 9 conductors, the ampacity must be reduced to 70%, and so on. These adjustment factors are cumulative, meaning that if multiple adjustment factors apply, they must be multiplied together to determine the overall adjustment factor. Another factor that affects the ampacity of conductors is the ambient temperature. The ampacity tables are based on a specific ambient temperature, typically 30 degrees Celsius or 86 degrees Fahrenheit. If the ambient temperature is higher than this value, the ampacity of the conductors must be reduced to account for the increased heat. The NEC provides correction factors for ambient temperature in NEC Table 310.15b2. These correction factors are based on the insulation type of the conductor and the difference between the actual ambient temperature and the reference temperature of 30 degrees Celsius. For example, if the ambient temperature is 40 degrees Celsius and the conductor has a temperature rating of 75 degrees Celsius, the correction factor would be 0.88. This means that the ampacity of the conductor must be reduced to 88% of its value as listed in the ampacity tables. In the case of parallel conductors, the derating requirements are even more stringent due to the increased heat generated by the proximity of multiple current-carrying conductors. When conductors are paralleled, They are typically installed in the same raceway or cable, which further restricts their ability to dissipate heat. To understand why derating is necessary for parallel conductors, it is important to consider the principles of heat transfer. Heat transfer is the process by which thermal energy is exchanged between objects or systems at different temperatures. There are three primary modes of heat transfer: conduction, convection, and radiation. Conduction is the transfer of heat through a material by direct contact. In the case of conductors, heat is conducted from the conductor to the surrounding insulation and the raceway or cable. Convection is the transfer of heat by the movement of fluids, such as air or water. In the case of conductors, convection occurs when air circulates around the conductors, carrying heat away from their surface. Radiation is the transfer of heat by electromagnetic waves. All objects emit thermal radiation, and the amount of radiation emitted depends on the temperature of the object. In the case of conductors, heat is radiated from the surface of the conductor to the surrounding environment. The rate of heat transfer depends on several factors, including the temperature difference between the object and the environment, the thermal conductivity of the materials involved, and the surface area of the object. In the case of conductors, the rate of heat transfer is affected by the number of conductors in the raceway, the size and type of the raceway, and the ambient temperature. When multiple conductors are installed in close proximity to each other, the heat generated by each conductor can raise the temperature of the surrounding environment. This increased temperature reduces the temperature difference between the conductors and the environment, which in turn reduces the rate of heat transfer. As a result, the conductors are less able to dissipate heat, and their temperature rises. If the temperature of the conductors exceeds their temperature rating, the insulation can begin to break down, leading to a short circuit or fire. To prevent this from happening, it is necessary to derate the ampacity of parallel conductors to account for the increased heat generation. The derating factor for parallel conductors is typically based on the number of conductors in the raceway and the type of raceway. For example, if there are 4 current-carrying conductors in a raceway, the ampacity of each conductor must be reduced to 80% of its value as listed in the ampacity tables. This derating factor is intended to ensure that the conductors do not exceed their temperature rating under normal operating conditions. In addition to derating the ampacity of parallel conductors, it is also important to ensure that the conductors are properly sized for the load. The NEC requires that conductors be sized to carry not less than 125% of the continuous load. A continuous load is defined as a load that is expected to operate for 3 hours or more at a time. This requirement is intended to provide a safety margin to prevent the conductors from overheating under continuous operating conditions. To properly size conductors for a given load, it is necessary to calculate the total load current, including both continuous and non-continuous loads. The continuous load is multiplied by 1.25 and then added to the non-continuous load. The resulting value is the minimum ampacity required for the conductors. Once the minimum ampacity is determined, the appropriate conductor size can be selected from the ampacity tables. It is important to select a conductor size that has an ampacity equal to or greater than the minimum required ampacity. In addition to sizing the conductors for the load, it is also important to consider the voltage drop in the circuit. Voltage drop is the decrease in voltage that occurs as current flows through a conductor. Excessive voltage drop can cause equipment to malfunction or operate inefficiently. The NEC recommends that voltage drop be limited to 3% for branch circuits and 5% for feeders. To calculate the voltage drop in a circuit, it is necessary to know the length of the circuit, the current flowing through the circuit, and the resistance of the conductors. The voltage drop can be calculated using Ohm's law, which states that voltage is equal to current times resistance, or volts equals amps times ohms. The resistance of the conductors can be obtained from the NEC tables. Once the voltage drop is calculated, it can be compared to the recommended limits. If the voltage drop exceeds the limits, it may be necessary to increase the size of the conductors to reduce the resistance and lower the voltage drop. In summary, the derating of parallel conductors is necessary to prevent overheating and ensure the safe and reliable operation of electrical systems. The derating factor is based on the number of conductors in the raceway and the type of raceway. In addition to derating the ampacity, it is also important to properly size the conductors for the load and to consider the voltage drop in the circuit. By following these guidelines, it is possible to ensure that electrical systems are properly designed and installed, and that they operate safely and efficiently. Remember that consulting the latest edition of the NEC and consulting with a qualified electrical engineer or inspector is always recommended for specific applications and interpretations of the code. Consider a scenario where you have a 480-volt, three-phase system feeding a large motor. The motor has a full load current of 380 amps and is considered a continuous load. You plan to run the conductors in a steel conduit underground for a significant distance. First, you need to determine the minimum ampacity required for the conductors. Since the motor is a continuous load, you must multiply the full load current by 1.25 380 amps times 1.25 equals 475 amps. This means you need conductors with an ampacity of at least 475 amps. Now, you need to choose between using a single conductor per phase or paralleling conductors. Let's explore both options. Option 1, single conductor. If you choose to use a single conductor per phase, you would need to find a conductor size with an ampacity of at least 475 amps from NEC table 310.15b16. A 750 mcm copper conductor, for example, has an ampacity of 475 amps when rated for 75 degrees Celsius. However, since you are running the conduit underground, you need to consider the ambient temperature. If the soil temperature is higher than 30 degrees Celsius, you will need to apply a correction factor from NEC table 310.15b2. Let's assume the soil temperature is 40 degrees Celsius. For a 75 degrees Celsius rated conductor, the correction factor is 0.88. Therefore, the adjusted ampacity of the 750 mcm copper conductor is 475 amps times 0.88 equals 418 amps. This is less than the required 475 amps, so you would need to choose a larger conductor or consider paralleling conductors. Option 2, paralleled conductors. If you choose to use paralleled conductors, you will need to determine the number of conductors per phase and the appropriate conductor size. Let's assume you decide to use 2 conductors per phase. In this case, each conductor would need to carry half of the total current. 475 amps divided by 2 equals 237.5 amps. Now, you need to find a conductor size with an ampacity of at least 237.5 amps before derating. A 3/0 copper conductor has an ampacity of 225 amps at 75 degrees Celsius. However, you need to apply a derating factor because you have more than 3 current carrying conductors in the conduit. With 2 conductors per phase, plus a neutral if required, you have a total of 6 current carrying conductors in the conduit. According to NEC table 310.15 cone, the derating factor for 4 to 6 current carrying conductors is 0.80. Therefore, the derated ampacity of the 3/0 copper conductor is 225 amps times 0.80 equals 180 amps. This is less than the required 237.5 amps, so you would need to choose a larger conductor. A 4/0 copper conductor has an ampacity of 260 amps at 75 degrees Celsius. After applying the derating factor of 0.80, the derated ampacity is 260 amps times 0.80 equals 208 amps. This is still less than the required 237.5 amps, so you would need to use an even larger conductor or increase the number of parallel conductors. Let's try using 3 1/0 copper conductors per phase. A 1/0 copper conductor has an ampacity of 170 amps at 75 degrees Celsius. With 3 conductors per phase, plus a grounding conductor, you have a total of 7 current carrying conductors in the conduit. According to NEC table 310.15 cone, the derating factor for 7 to 9 current carrying conductors is 0.70. Therefore, a derated ampacity of the 1/0 copper conductor is 170 amps times 0.70 equals 119 amps. Since you have 3 conductors per phase, the total ampacity per phase is 119 amps times 3 equals 357 amps. That is still less than our 475 amp requirement. As you can see, determining the correct conductor size and derating factors for parallel conductors can be complex. It is essential to carefully consider all the relevant factors, including the load current, ambient temperature, number of conductors in the raceway, and the NEC requirements. Always consult the latest edition of the NEC and consult with a qualified electrical engineer or inspector to ensure that your electrical system is safe and compliant. The NEC doesn't require the use of derating factors, but it recommends that they be used in order to ensure that the conductors are not overloaded.